We wanted to say hi this morning. All right. So I'm going to do just the first example with you guys. There are 2 examples in the notes for today. You definitely need your calculator. So if you don't have it yet, get your calculator out. There might be a few spots in the video where you're going to want to hit pause so you have time to enter everything in yourself. So just as a little heads up. All right. So it's saying since sine and cosine differ by only a phase shift, meaning you just shift it over and then it's a sine curve or a cosine curve, you can model anything using sine or cosine. So with that being said, the calculator only does sine regressions because anything that can be modeled with cosine can also be modeled with sine if you just shift it over. All right. So the example, and nothing's more fitting as I'm sitting in my porch and it's snowing outside right now. Talking about the average monthly temperatures. Oh, Rochester's killing me right now. So they're telling us the month of the year. So like month 1 would be January and February and so on. And then this is the average temperature in Fahrenheit. All right. So you got to think lows and highs of the day. This is the average temp. So even the highest temps are only going up to 74 because it gets kind of cold at night. Right. And then wintertime, you can see it's more down in like the 20-degree mark. So it says graph the data on the axes provided. And then we're going to create a model to represent what's going on here. Right. So first things first, on your x-axis, that's the time from 1 to 12. On your y-axis, that's your temperature. So I would like you, even if you have to pause the video, if you don't have enough time, I would like you to take a moment and plot the points, all right? So it doesn't have to be perfect, but it should be reasonable, you know? So like 37.9 degrees better be somewhere between 35 and 40 when you plot it on the graph, all right? So take a few minutes, get all of that plotted on your graph. And then we'll take it from here. So 7, let's see. So this is usually a day that's really fun to do in class together because we actually work out the equations as a group with kind of some feedback and your input. So unfortunately, all you're hearing from today is me. So you're going to have to agree with me because you have no other choice. But basically, that's the idea. All right, so once you get it graphed, I want you to draw a curve that goes through it to the best of your ability. Okay. So what you should be starting to see is kind of that sine curve showing up, or cosine curve, whichever way you want to think of it. But the idea is that if this were to repeat itself, if we were to keep going, and then it would come back up, and back here it would keep going, and so on. All right. So when it says graph the data, there we go. Bam, did it. Find a model. All right. The details that you need the amplitude, the frequency, the phase shift, and then the vertical shift. So we actually are going to be looking at a phase shift here, but I'll explain it more in a moment. All right. Even though it seems like we're going backwards, I actually want to start with the midline. Because if we can figure out where the middle is, it kind of helps us determine everything else from there. So the midline is always the average of the minimum and the maximum values. So take a look at your chart up above. The lowest temperature is happening right here. There's your minimum value at month 1. Your highest temperature right here at 74. All right, let's average those two. So if we do 23.8 plus 74.0 divided by 2, that's going to come out to be 48.9. So on your graph, I want you to go over to 48.9 and draw in that dotted line for the midline. So just below 50 is where that midline is. The things that we can now figure out, right? What's the amplitude? Well, the amplitude is the distance from the max down to the midline or the midline down to the bottom, whichever way you want to think of it. So I'll take our maximum of 74.0 and subtract that midline of 48.9. That's going to give us a difference of 25.1. So that's that stretch right there. So now we've got our amplitude. All right, think about the other values that we need. We need to figure out the frequency, and then we need to figure out the phase shift. Let's talk about the frequency first. Frequency is really going to be based on the period itself. So if you think about what's the period of the graph. Now, this isn't totally perfect, but the idea would be that once you get back to January again, you'd be right back down. So like, let's pretend January would be month 13. We'd be right back down to here again. Okay, thanks, buddy. And so I would say that the period is going to be 12 months. All right, it makes sense that 12 months later, you're back right where you started. So if we set that equal to 2 pi over b, we could quick cross multiply. And you could divide by 12. Guys, take Teddy outside. And then b comes out to be pi over 6. So that's the frequency. All right. All right, last part. As for the phase shift, to me, right now to me, it looks more like a cosine graph. It starts at the bottom, goes all the way up. So like a negative cosine graph. What I would suggest, though, is we want to make it a sine curve so that we can compare it with what the calculator is going to give us. So for this to be a sine curve, it needs to start on the midline. So take a look at the graph. Sorry, we got a lot of parts moving around my house today, a lot of sound going on. And for it to start on the midline, I would say, let's start the curve right there. And then it would go up and down, and then somewhere over here would come back up and it would finish the curve, all right? And I'm assuming that that's going to take about 12 months to come back to that point. Right? So what does that mean? Well, instead of starting at 0, where would we start at? Well, if you look on my graph, it almost perfectly falls right at 4. And if you look at 4, look at that, 48.9, which matches the midline. Woo, how perfect we are. All right, so what that means is that the phase shift, we're going to have it shift over to start right here at 4. Okay, let's build an equation with that. So we've got all the values. So y equals 25.1 times sine of pi over 6, parentheses. And now if I want it to go to the right 4, remember what that means. It needs to look like the opposite. So it's going to have it as a minus 4 inside of there. Right? And then close up the double parenthesis, and then plus the midline of 48.9.
That did not go well.
That should be the equation of what we have right there. All right, now let's test it. So on your calculator, I want you to go up into your y equals, and let's, hold on one second. Guys, make sure to clean them up and then back into the other room, okay? Thank you.
It's because,
all right,
he
Gracie.
kept running to the side of the house.
Back into the other room, okay?
Mm-hmm.
All right. So let's type in 25.1, woo, and then sine of pi over 6. And then, whoops, I think I got an extra parenthesis going on there. Let me get rid of that. Pi over 6. Now we can use a parenthesis. X minus 4. And then close that up. Plus 48.9. All right. So make sure when you type it in, everything's typed in carefully. You should still be in radian mode. I'm going to switch my window before I graph it so that it goes from 0 to 12. You could make it go to like 13 or 14 if you want to see more. That's fine. All right. My scaling, you can stick with 1 or 2. It really doesn't matter. All right. Your Y minimum, I'm going to start at 0 just like this does, but I'm going to have it go up to 80 to make it match the graph that I'm looking at. Right? And then I'm going to do tick marks every 5. Okay. Hit graph. Let's see if it matches what we have here. That is actually looking pretty darn good. If I want to, could I even type in the midline of the 48.9? Sure. Oh, look how pretty. And there it is. Okay. And you can see right there, mine were tick marks of 2. So let me see if I can zoom in a little bit. So here's 2, 4. At 4, beautifully hits that midline. So we were pretty dead on with our equation. Okay, now here's the new part. Other than just having practice with creating the equations, we're going to actually do a regression to see would the calculator give us the same thing. So to have the calculator do the regression, this is where we've got to put it into the lists. So what the X is always goes in list 1. What the Y is, that's going to be list 2. Now I already put it in the calculator, so feel free to hit pause and put it into your calculator so that you know how to do it. All right, if there's anything already in your list, clear them out. So you go to stat and then edit, and then you can clear it by going up top and hitting clear. Otherwise, type in 1 to 12 in list 1, and you're going to type in all the temperatures in list 2. Make sure they are accurate. All right. Now let's do the regression. So it says, use your graphing calculator to obtain a sine regression model for the data. Round the coefficients to the nearest tenth. All right, so you already did stat, edit, and you put this stuff into list 1, list 2. So that's a little reminder for the first part. Then you're going to go to stat, and then calculate, and then C is the sine regression. So you can arrow up to get there or arrow down. It does not matter to me. All right. So let me do it on my calculator so you can see it. So you're going to go to stat, go over to calculate, and then I'm going to go up, and choice C right there is sine regression. Now what it's going to default to is the number of iterations is 3. Just leave that there. That's perfectly fine. Don't change that. X list is L1, Y list is L2. That's perfect. And don't put anything in for the period or storing the equation. You don't need it. So just hit enter. And then what it should give you is the values for the amplitude, the frequency, the phase shift, and the midline. Now, the only thing that's a little bit different here is they don't have that extra set of parentheses, which means the B value's kind of been distributed. But let me explain that in a moment. So let's write this down first. So what we end up with here, let's see, is our equation of y equals 25.2 sine of 0.499 would round up to 0.50. Oops, nearest tenth. Got to read my directions more carefully. So we'll get rid of that O there. So 0.5 and then x and then minus 2.0 and then out here plus 48.7. All right, so that's the equation the calculator gives. Let's compare the two. All right. We said 25.1 for the amplitude. They said 25.2. It's pretty darn good. All right, pi over 6. If I do pi divided by 6, that's 0.52. That pretty much matches our 0.5 right here. All right, what I meant by the distribution is if I distribute that pi over 6 times -4. So I'm going to multiply that by -4. This would have been about 0.5 here, x, and then minus 0.2 or negative minus 2.1. Okay. All right. Which matches our 2.0 pretty close. And then they had 48.9, or excuse me, we had 48.9. Calculator came up with 48.7. So the whole point is we're pretty darn smart right there. All right. Oh, when it says, what do the two models you created predict for the average temperature in June? All right. Well, we know what the temperature should be in June. June is month 6. So this should be June right here. So it should come out to be about 68.9 degrees. But we're saying, what do the models predict? So let's use our model versus the calculator model and see who's more accurate. So our model, we're going to plug in x equals 6 and see what happens. So if we do 25.1 sine of pi over 6, and then right here, we're going to plug in 6 minus 4, and then plus 48.9. And we can do all that right on the home screen. Right? So nothing crazy. So 25.1 times the sine of, and then type in pi over 6, and then times 6 minus 4 is really just 2. Close that up, and then add 48.9. That gives us 70.6 degrees. So about. All right. So this is the temperature prediction for June. All right. Now let's look at the regression model. All right. So the calculator model. We're going to do the same thing. You're going to plug in. So 25.2 sine. This is going to be 0.5 times 6 and then minus 2.0 and then plus 48.7. So you can grab your calculator. Otherwise, you can do it along with me just watching here. So 25.2 and then sine of, in the parentheses, 0.5 times 6 and then minus 2.0. Close that up, plus 48.7. And this model gives 69.9 whatever. So we can say like 69.9 degrees. So this is the temperature for June based on the calculator model. Now, which one should be more accurate? It should be the calculator. Even though we're super smart, the calculator is using the actual data and can get, a little bit more accurate versus our just graphing and estimating from there. So it's supposed to be 68.9. So the calculator model's off by about a degree. We're off by about 1.5 degrees, not even 2 degrees. So it doesn't see which one's better. It just said, what did the models predict? In either case, the models are pretty darn close. It's never going to be 100% perfect because you have to remember, this is a lot of data. The chance that it's going to hit every point perfectly, highly unlikely, all right? Because think about from year to year what the temperatures end up being. Might be a little bit of a warmer year, might be a little bit of a colder year. So it might not perfectly fit that flow, but it should still be approximate that it's kind of going up and down and following a sinusoidal pattern. All right. The backside has another question very similar to it. On the website, we'll have like all the answer key to this one. So this is my copy that's already done, but feel free to take a look at it there. So I do the same thing where I plot it just by hand, nothing super fancy, and I estimate what it's going to be. And then I let the calculator do it and I compare it. Thanks, guys. Have a fantastic rest of your day.